So good afternoon. I want to welcome you to our talk on BinaryPig, a system that we built for performing large-scale processing and analysis on small binary files, especially malware, over Hadoop. My name is Jason Trost. This is Telvis, Calhoun, and this is Zach Hanif. We're from Endgame. Endgame is bringing data science to cybersecurity, allowing you to sense, analyze, and act against threats in real time. Here's the agenda for today's talk. First, we're going to discuss the problem that we aim to solve, which is there's tons of malware and we want to be able to process that malware to keep up with it. Then we're going to cover the architecture of the system we built to solve this problem. We're going to go into some code and implementation details, really details so you know how it works, and then also how you can use it if you're interested. Then we're going to cover some analysis of results of processing roughly 10 terabytes worth of malware using this system. We're going to give a demo of the web application portion of this system that we're going to open source today. And then after that, we're just going to wrap up. So this slide sums it up pretty well. Malware infections have been growing tremendously over the past 10 years. At Endgame alone, over the past 2.5 years, we've received roughly 20 million samples of malware, equating to roughly 9.5 terabytes worth of malware. So 9.5 terabytes. This is a huge amount of data. In this, we are not alone. McAfee and Kaspersky both report they receive roughly 100 to 200,000 pieces of malware per day. So this problem is tremendous. A little known luminary from Brooklyn actually had some similar problems and he summed it up quite nicely. So you might ask, what do we do with all this malware and why is it useful? Well, malware data mining is actually pretty useful. We use it at Endgame for improving our threat intelligence feeds. So, anything that's related to malware, it's really good to have detailed information about the malware. We use it for contextual enrichment of events. So if you have a DNS lookup or an HTTP callback, and being able to correlate that back to known malware is actually really useful in the course of an investigation or some sort of forensics event. And then lastly, we use this huge corpus of malware for building machine learning models that we can use to then do better rapid triage of new malware samples and then just better detection of new malware samples, because most of the malware we get, frankly, is not detected by any antivirus. So now I want to cover the old architecture that pretty much the old way we used to handle processing malware. In this picture we have a ton of malware samples, all stored in NFS. We use a compute cluster which consists of several servers that all mount NFS, and they process the malware, and then that data gets stored into a relational database. If you've done any large-scale data processing over the past 10 years, this architecture might look familiar. It's a pretty standard, like pre-Hadoop, large-scale data processing architecture. But this architecture actually had a lot of problems as we started to throw more and more malware at it. We really had two problems. So we wanted to be able to process the daily dumps of malware we get in, and we also want to reprocess all the malware that we have in our corpus. If we have a new idea, have a new query, want to extract some new intelligence out of the data that we hadn't done before. So using this architecture for the latter problem turned out to be pretty problematic as we got into the terabyte scale. So NFS turned out to be a big single point of failure. So if NFS went down, we couldn't process any of the malware, which was a problem. It was also a major bottleneck. We found that as we're processing this malware, even if we added more compute nodes to the compute cluster, we reached a point where we just stopped seeing increases in performance, and this is really bad, right? So most scalable data processing systems, you want to just be able to add new computers to the system and have it scale linearly, but that wasn't happening. And then lastly, it provided very poor data locality. So the data had to be copied across the network every time we wanted to process this malware. NFS does do some caching locally, but it really didn't work very well for the problem we were trying to solve. Next, the compute cluster had some problems of its own. Like I just mentioned, very poor data locality. So the processing time gets dominated by copying data off the disk of that one NFS server and then across the network. That's really bad. If a compute node went down during this processing, especially for processing a huge batch of malware, knowing which malware that compute node was processing and having to reshuffle that to the other machines to process it was a huge headache, and just in the end turned out to be too hard to manage. So it didn't work well for this problem. And then lastly, we used a relational database. This worked pretty well at the beginning when we had a fixed set of analytics, but we really wanted to be able to iterate quickly, create new scripts for extracting new information out of the malware, and be able to store this data and have applications leverage this data. Relational database was really not agile enough. A lot of the data that we have is highly nested or object-oriented. So storing this in a relational database means you either have to create new relations every time you create this new data, or you just store it as a big blob, and both are really not ideal for doing rapid iteration, rapid development. So really what we needed was a system that scaled to our historical data set. So being able to go back and process 10 terabytes worth of malware, trying a new static analysis technique. A system that recovers from failure. So if a node goes down or if we lose a drive in a server, the system as a whole should continue to function and continue processing the data really without much manual intervention. So we shouldn't have to go try and determine which malware needs to be reprocessed and manually shuffle that. A system that grows through scripting. We really wanted to make sure that our malware analysts could just write the simple, relatively simple Python scripts that really focused on the malware and did not have to focus at all on the scalability part of this problem. This allows us to leverage our pre-existing tools as well as any open source tools that process malware, such as PE frame is one that comes to mind, the one that we actually ported to this system. One that we also wanted to be able to support dynamic schema, so that highly nested or object-oriented data, we wanted to be able to query and retrieve records based on the fields or based on the values in those fields and have it work well. And then lastly, we wanted to be able to search it via web application. We want to be able to build on top of this, so have an API so other applications could be built on this data. So we built it, and we're talking about that. We're going to talk about this in greater detail. Our system is called BinaryPig. It's a framework for processing small binary files using Apache Hadoop and Apache Pig. Now I'm going to turn it over to Telvis, and he's going to go into greater detail.
So we built this, So we built this to be a collaborative tool, not just something we slung together just for Black Hat, but a tool that everyone in our organization can build on top of. So we had 4 basic requirements. First, it has to have a simple API, right? Like if there's a large barrier or a high barrier to entry, people aren't going to use it. The second, it has to have pluggable analytics, right? So it needs to be modular. You shouldn't have to reinvent the wheel in order to get all the benefits that you're getting from BinaryPig. The next has to play nice with existing tools. So we assume that everyone already has analysis scripts that are doing static analysis, right? So what we want to do is make it as easy as possible to just hack your script a little bit, just a few lines, to integrate it into our system. And finally, a rapid iteration. So the goal is to have our 10 terabytes of malware to be able to process that quickly, right? So you create your new analysis scripts, and instead of it taking a week to see if your script works, you can, depending on the size of your Hadoop cluster, it could take a day or it could take 5 hours or 1 hour depending on how much capacity you have. All right, so we're going to discuss our architecture for BinaryPig. So we're going to answer 3 questions here. First is, how do we store the data? How do we store the malware in Hadoop? The second is, how do we process the data in Hadoop? And then finally, how do we explore the results? So storage. The first thing we want to do is we need to put the malware binaries in HDFS, right? So HDFS isn't really intended for a bunch of small files, so you have to aggregate them into one large file, and we do that using sequence files. So basically we aggregate them into one file, and we have scripts that'll do that for you, and then you push that sequence file onto HDFS, right? HDFS has lots of really cool features that are really good, that solve some of the problems that Jason talked about before. First is replication. So if we have a node that goes down, it's not the zombie apocalypse, right? Like we're not losing any samples. That data is replicated. It'll get re-replicated if that node goes down. The second is horizontal scalability. So as our malware zoo grows, it's horizontally scalable, so you can just keep throwing nodes at it, and it can support 10 terabytes or 100 or as much as you have. So So next is processing. So this is built on top of Hadoop. Hadoop is a scaling, processing framework, right? So how do we run static analysis over Hadoop? We do that by extending Apache Pig. Apache Pig is just a scripting language. When you execute Pig, it is transformed into Hadoop jobs. So by extending Pig, we run over Hadoop. So that's how we do it. And one advantage of that, is data locality. So before we had we had the transfer of malware binaries from NFS to our compute cluster. No more of that, right? So all the data is data local, and when the MapReduce job executes, the binaries are written locally, and it processes them locally. There's no shuffle, there's no overhead for that, and because obviously that overhead is expensive the more samples you get. And data exploration. So really, when you have this scale of data, right, of malware, it's kind of worthless to be able to analyze it when you can't explore the results. So to explore the results, we have a simple application that does powerful searches backed by Elasticsearch. So Elasticsearch, you can do free text search. It's all loose. It's just a wrapper on top of Lucene. So we assume that the output from your analysis is free text or structured text. We put that into Elasticsearch. Elasticsearch speaks JSON. You can just throw it at it. It's really simple. That's why we used it. And then we have a simple app that we'll demo later. We use Elasticsearch, but the system isn't tied to Elasticsearch in any way. That could be Accumulo, that could be HDFS, that could be back into HDFS. It could be anything you want there. So don't get the impression that it has to be Elasticsearch. It absolutely does not. The one caveat is it needs to be a storage, has to have storage capability from Pig, since BinaryPig is written as an extension to Apache Pig. So why write another framework, right? So everyone here knows there's tons and tons and tons of open source tools for doing malware analysis and open source tools built on top of Hadoop. So why write another one? So the first is all the static analysis tools aren't made for scale, right? They're made for, one hacksaw at his desk with a few samples. You run them in a simple script. It's not made, none of them are made for, terabytes of malware. The second is Hadoop isn't made for processing a bunch of small malware files, right? And the third is there's no simple combination of the two. There's no just put the binaries on Hadoop and it'll magically work. So we had to build a framework to do it for us. So now we're going to look at some code. And we're going to demonstrate how you can do malware analysis at scale and make it as easy as the slap chop. All right, so the first thing you want to do, like we said before, is to create the sequence file. So we have a couple of scripts. We assume you already have a malware Zeus somewhere that's either on disk or in an archive. So we have two convenient scripts that will take your archive or your subdirectory and copy that up to, generate that sequence file and copy it up to HDFS. Like I said, note on the sequence file, for those that aren't familiar with it, it's just a simple data structure. The key, we make the MD5 of the malware binary, and then the value is the actual binary data itself, right? So that's what we copy up. Then when you run it over Hadoop, when it iterates over each line is an MD5 and the malware. So the loaders, so most of the magic happens here in the loaders. We need to do some background on Apache Pig. So in Pig, when you want to read data from HDFS into your script like workspace or into your namespace, you need to do a load command. And load, you just give it a path and it reads that data from HDFS and does whatever it needs to do in Hadoop land, and it makes it visible to you in the Pig script. We basically extended that so that it will take your malware, it will extract your malware binary from the sequence file, write it to disk, then perform your analysis on that binary that was written to disk, and then give you the results back in Pig. So you just pointed at a bunch of malware, and what you get in Pig are the results. So you perform the static analysis at scale. An emphasis that this is a MapReduce job, right? So this is at scale. This is, if you've got 10 terabytes, 100 terabytes, petabyte, whatever. It's a function of the capacity of your Hadoop cluster. So we have two loaders, right? So in order to execute the load, we'll either execute the static analysis script and just read it directly, just run it one at a time. Or we can have the daemon loader. And the daemon is specifically for cases when you're doing static analysis that requires signatures. So something like ClamAV, for example. So if you need to run ClamD or ClamScan, it needs to load 20 meg of signatures. You don't want to do that over 20 million samples. The overhead is prohibitive. That's what we did at first, and it was a lesson learned. So as a workaround, we have a daemon loader, and it assumes that you've set up a daemon you deployed this daemon on all of your worker nodes in your Hadoop cluster. And all it requires is a simple connection with the path of the file. It's going to receive that path. It's going to perform the analysis and write it back over the socket, and that's what gets patched back up in the pig. So as far as you're concerned, all you care is that you wrote a simple script, some magic happened, and you have results. And it's up to you to determine what you want to do with it. So some optimizations. So first, when we looked at the first implementation, it was a bunch of network copies in order to get it to the compute cluster. So at least now we have data local, but we still have scripts that expect file paths, right? So we have to extract the data from the sequence file and write it to disk. So that's not free either, right? So a workaround for that is to use devshim. Devshim is just memory mapped, file space. So it looks like a file for the purposes of any script, but it's actually in memory. So presuming you have enough memory to support, all of the mapper nodes, all the Hadoop processes, then you could just write them all to devshim. It's as fast as writing to memory, and it runs fine. And the second we've already discussed is the daemon loaders. The first time we ran, our BinaryPig over all of our samples for ClamD, it took quite a while. And a lesson learned was if we can just load those signatures once, have a daemon perform the analysis, you save, it cuts it down in half almost. You'd be amazed how much time you save having an actual daemon there. So this is a list of all of the loaders we have in BinaryPig right now. There's a generic script loader we'll look at. It's just a regular script like you would run, a simple bash script or Python or whatever you like. The daemon loader we just discussed. And then we have 3 implementations, so ClamAV, Yara, and PE hashing. An emphasis on ClamAV. We're not endorsing ClamAV in any way, but it's free, it's open source. We presume that anyone that's getting that's using our framework can get access to it. So if you just want to set it up locally and run it, everybody should be able to get Clam. So that's why we use it. All right, so we're going to show in 5 lines of code how you can analyze malware at scale. So the first thing is to create a simple bash or simple script, and everyone recognizes this. This is just strings. This extracts all the strings from a binary. It takes the file path. The next we have a pig script. So for people that aren't familiar with pig, we'll walk through it. The first thing you need to do is define the loader we're going to use. Here we're using the executing loader. Like we said before, this is the non-daemon one. Every time you run this, it has to do all of its initialization, which is fine if we do something like strings because there's no signatures. The second is the load command. So that's what we talked about before with, that is what actually executes the Hadoop job. We'll read your malware from the sequence files, perform the analysis in that Hadoop job. And this is all parallel, all at scale. It works for however many nodes you got. The emphasis here is on that, right? Like before you were running on, a bunch of scripts, like one-offs. Now you can analyze as much as Hadoop capacity, right? So that's awesome. It changed our world, and hopefully it'll be useful for you all. And so that's the load statement there. We get an alias to where it puts that data. In data, I guess when you run load, what you get back are the results, right? So you get all the strings from that binary. And finally, the dump command is a print, write the standard out. In our examples, we write to Elasticsearch there, but replace dump with whatever your favorite NoSQL store is, and we can write to it. It leverages everything you get in Pig, but extended so that you can do malware analysis over it. All right, and really this is really simple. It's a file and a script. So anything that works over a file and a script can work in BinaryPig, right? So we can do image analysis, we can do a PDF extraction, any of these, anything you can think of that's just a file and a script. We're doing a talk on malware here, but it can literally be anything. And we have a simple web interface that performs really, really powerful queries that we'll demonstrate later. A simple app, everyone here recognizes Twitter Bootstrap. That's what happens when you get backenders writing UI code. But it's really awesome because it allows us to do free text searches over all of our data. So we don't know what strings we've extracted, right? So now we can just do searches for Java or searches for Dalvik or anything, and we get the results. We don't have to grep logs. We don't have to write any more parsers. Elasticsearch is, it's Lucene, so you can do free text searches, faceting, anything you want to do. It's really awesome. All right, and I'm going to hand things off to Zach and Becky.
So obviously we've been using the system internally for some time, and we've developed some results, and we're opening them up and we're sharing them now. Going back to the original part of this presentation, our historical data set is around 20 million unique binaries. 94% of them are in the PE format, about 6% are Android APKs and various things that run on the Dalvik JVM. And then there's some minuscule fraction left over that represents Macromedia Flash, PDFs, all sorts of other detritus that tends to get collected all at once. At the time of developing this system, we were running this off of a 15-node Hadoop cluster, and it would take us about 5 hours, give or take depending on the specific scripts that we were using, to run over the entirety of our historical set. This is obviously compared against the previous system that we had implemented, where running over a historical data set was completely time prohibitive, if it was capable at all, due to random hardware failures and a lack of robustness overall. It has seriously helped our ability to develop new analytics, apply them to a historical set, and then learn and continue progressing beyond that. I mean, no longer do we develop something new and can only apply it going forward with our daily malware ingest. We can actually re-ingest all of our systems and then continue moving forward with the new material. And this has been a huge help. So we've got some general findings, and these are probably very difficult to read, but that's perfectly all right, because when we went into this, we were hoping to find something incredible. We were hoping to find one big thing that challenged all of our previous understanding of malware. And unfortunately or fortunately, depending on how you look at it, none of the basics really were shocking. We found, a few evidences of, our primary contenders for languages used in various resources, or imported DLLs, or the average size of various files. But these were all things that we intuitively knew beforehand, which was interesting. I raise this now because, when part of what we started realizing was the ability that we had to rapidly develop new analytics was incredible. We could run a single day's worth of malware in the span of about 2.5 minutes, 3 minutes. We could run a week's worth in around 10 or so. It was an absolutely earth-changing event for us internally, because we were able to very quickly explore every aspect of the data that we had and go through it and look at it again and again and try new things. So after realizing that the very basics of malware census taking was not going to give us anything earth-shattering, we started to move to more advanced feature extraction. And our core motivation here was to drastically improve the experience that we had for developing new and validating our internal research. So one of the first things we started with, and there's a great deal of academic papers and work already been done on this, was feature extraction to identify individual packers. We would extract things such as overall and sectional entropy, the overall Kolmogorov complexity of various elements within the PE headers and the PE files themselves, individual sections and resource names, section flags, import tables, function calls, and just everything else that we could find. It really became a huge thing to try and extract and compute new features and new elements because it was so trivial to do so. I think all in all we've extracted over 550, 560 discrete individual features from the PE files that we have. And we've definitely been able to do a lot of work with them. We found internally that we've been able to develop a number of models that allow us to detect very, very easily whether or not we have a set of packers that fit into some of the major families, the UPX families, Themida, VM Protect, all of the other big popular ones. We've been able to find this with fairly high reliability, and it's been a necessity for us because in a lot of our work and research we've gone back and questioned repeatedly the use of PEID and other such tools that rely on signatures. PEID specifically, the majority of their signatures are 5+ years old now, and developing new signatures for that is a manual process. What we were attempting to do, and I think I can say we've succeeded at, was the ability to easily cluster individual elements and individual pieces of malware that are packed with various families of packers, and be able to quickly triage them internally to figure out what we need to go through before doing deep dive analysis. So I've mentioned a couple of features coming out of the PE header, and we're fully aware of some of the weaknesses inside of the PE header itself. These features are shallow, and these features are easily manipulated by malicious authors, which of course when you're analyzing malware, that's really all you have in front of you. We're fully aware that this is less resolution than individual reverse engineering features, but we found repeatedly that the ability to apply mass amounts of data in a statistical learning model has definitely given us an advantage. It really comes down to the unreasonable effectiveness of large sums of highly entropic data. A couple of things that we found that we determined were fairly interesting. For a lot of the malware that we have, the headers themselves were never manipulated. Even things as basic as manipulating the time of compilation inside of the PE header was never manipulated for a large percentage of our samples. We certainly found that when developing our clustering algorithms and our other triage mechanisms, which was a major reason for doing this, we learned very quickly that we would have to ignore some of the tighter clusters and go for some of the wider ones. When doing all of this clustering work, one of the big lessons we had to learn very, very quickly was you need to be certain that the clusters that you're getting out are representative of the features that you're using to do the clustering. If you attempt to read into too much, if you attempt to assign meaning to something where meaning doesn't exist, you can get very strange results very, very quickly. So some of the results we've had so far, everything we were doing in our initial stages were to perform dynamic analysis winnowing. With the amount of malware that we get per day, the only way to scale our dynamic analysis systems was to add more and more hardware, which would increase our time burden on the IT teams and people who run the dynamic analysis systems and maintain it when it breaks and all sorts of other things. And one of the big things we've been trying to do recently is try and winnow things down so that if we can only run a handful of representative samples, we can run them for longer. We can perform more complex analyses inside of a dynamic space. Our largest cluster that we've been able to find and determine and do some validation on was over 300,000 samples. There were 3 major malware families contained within. This was a very large cluster based off of certain elements of highly virulent polymorphic families. Our second largest was significantly smaller, and it tapered down into a long tail fairly quickly. What we've been able to find out of this with pretty high reliability, because we've run all of these samples so far through our dynamic analysis system, is that our accuracy is really quite good. We're still going through and we're still doing additional validation on our results, and we're not quite entirely prepared to come up and do an academic talk about how exactly we've been able to go through and do validation. And that's another big thing that we've learned from using the system. With all of this data, with all of the information that we're able to extract, we have to go through and validate every single thing repeatedly. And a lot of that becomes manual efforts when you're trying to seek ground truth inside of a malware data set. Like I said before, the validation is certainly very tricky. You can't simply go off of antivirus results because they change over time. Different AVs don't necessarily always agree with each other. And of course, your cluster meanings will change as you develop your feature set, modify your feature set, and continue to evolve your analyses. But despite the fact that validation often becomes a manual process, it can be somewhat slow. The fact that we're able to do so much extraction and test so many theories so quickly with the ground truth stuff the ground truth information we have from the dynamic analysis that we have already done has been an enormous boon internally. One of the more interesting things that we've been able to do that we flatly couldn't do before was do icon extraction from individual binaries. Now this was something we actually started just for fun, just to see what would come out of it, and we ended up getting fairly good, strong results. If you take a look at these, every single one of these are things that have been extracted from real ground truth confirmed malware. And if you look at it, you'll probably see a handful of icons that are familiar to you from your own reverse engineering, and you'll probably see a few other icons that I think many of us internally would classify as malware, despite the fact that large software vendors would suggest are otherwise. This was just an interesting slide because of the fact that BinaryPig would allow us to very easily extract binary data from the resources and other elements of the binaries themselves, work them back into the system, and continue to do analysis on them. So we'd go through our binaries and various droppers and other malware families that we had. If there were PE files that were contained within the resources, if there were additional icons or cursor elements contained within the resources, or documents, or whatever individuals can put in there, and we were shocked at just how much they can put. We were able to take them out, create additional scripts for them, and continuously feed that into the system. So, starting with 10 things to analyze, we'd end up with 15, and then 20, and then 25, and we'd keep going from there. It was certainly an excellent process, which was very simple due to the framework that we've developed. So a couple of the features we pulled out of the icons because that was something fairly interesting for us. We did a lot of clustering based on them, mostly on the principle that icons are something that an individual author has to put in on their own. It's not an artifact of the compiler. It's not an artifact of the system that individual things run on. It's something that the author has to include of their own volition for many of these cases. And we extracted a number of pixel-based features for brightness and color values and pixel density, and we attempted to do clustering and feature extraction on that. We've also found that we've had excellent results doing cryptographic and fuzzy hashing on the files themselves. Individual icons we found will be spread across multiple families, and you can trace a certain amount of family lineage from that. And what we found over time is the fact that when we take individual files from what we believe to be a new malware family coming up and evolving, as it starts to gain traction, starts to gain speed, as we see more and more samples coming in from that, we'll start to see copycats get created, copying similar resources and such things. It's been something that we found. We're trying to figure out exactly why that is the case, if that's an artifact of the way we're doing clustering, if that's something that's reflected in real life. Again, validation becomes a manual process with a lot of reverse engineering. So we're moving through that right now. This is a lot of material that I've previously stated. Method of infection can definitely be extrapolated fairly easily. You see a lot of obfuscated executables, EXEs masquerading as PDFs and other such formats. You definitely get a lot of indication that people are attempting to do phishing elements. For some of our malware resources, for some of our malware ingest mechanisms, we know where the malware came from. We know how it attempted to enter a network. And we can definitely do a lot of correlation between multiple points. And it's been something that's been very useful when tracking large campaigns, when tracking individual families, and attempting to go all the way down to modus operandi of individual authors. So a few lessons learned that we've had from developing these models. Feature selection, as I said, is definitely a rabbit hole. We found way over 500 features in the PE header alone. We're developing more constantly, and a lot of the work that we are doing now that we've got this embarrassment of malware data, we're slowly winnowing it down and focusing solely on the high value, high gain information that we have. The abundance of features, as I said, definitely requires pruning. The interpretation and validation of results is something that is always a concern when developing statistical models. Manual validation so far is still an unfortunate reality, despite the fact that we can do large amounts of mergers with outside data sets, not just data sets that are developed using BinaryPig, but data sets from our dynamic analysis system, for our individual verse engineers efforts, from things that we hear from third parties. And care definitely has to be taken when interpreting unsupervised learning to make sure that we're getting meaningful results. So now we're going to do a short demo of the web interface that we have, and that should give you an idea of the tool that we're releasing very shortly.
So this is Google Chrome just expanded to full screen. This is the web application that we're releasing open source. So when you open BinaryPig, this is the screen you're presented with. It's a minimal Google-like search interface. Allows you to search on any of the fields that you extracted out of any of the data from any of the analytics that you ran, or you can just perform just simple free text searches. Across the top, we also have these tabs, and I'm going to go through them one by one. Each tab represents the collection of results from a particular processing module. So we have Yara is one of the modules we have. We have one for ClamAV, we have one for PE hash, and one for PE frame. In each of these tabs, we have taken out fields that we thought were interesting and fields that we thought might be worth exploration. We've pulled those fields out into facets, so you can see what's the most popular value in this field across this data set. And these numbers look small, and that's because this is all running on my local laptop. This is just a very reduced data set for the sake of a demo. Just keep that in mind. So here with Yara, the namespace is really the name of the signature set that we're using, and then the actual signature that matched the description. With ClaimAV, the only thing that's of interest is really the result. So is it a virus or is it not? And if it is, what's the category? For PE hash, we have the PE hash calculation. If you're not familiar with PE hash is an algorithm that takes specific pieces out of the PE header, hashes them together using MD5?
The P hash creates a large bit string, which is then hashed into MD5 for analysis.
So this is a malware clustering algorithm. So it's used to cluster malware that has very similar properties in its PE header. And then we also have the the output of the file command, so file magic. So we just can tell how many of these files we have. And then lastly, we have PE frame. PE frame is an open source tool that does a handful of different static analysis operations. We took PE frame on GitHub, we forked it, and we just made it output JSON so we can easily take the data and get it back all in a very nice structured format. So this is the output of PE frame. So these are all faceted rollups on this data. One thing I haven't mentioned so far is all these faceted rollups allow you to launch searches. So if you want to see all the UPX data, you just click the link and it launches a search for you. So we're back to that original search interface that I mentioned before with a preloaded search, which you can then look through these search results and further narrow your query by clicking any of these values. So let's just click one of them, and it allows you to iteratively reduce the data set that you care to look at. I have some interesting ones up preloaded. So this really just shows off, we support wildcarding. So with this, we're looking at the ClaimAV data, all the ClaimAV data that shows the trojan.spy.spyeyes -star, because there's a bunch of these categories. We also pulled up some Dalvik files. So Dalvik is the Android executable file format. So these are basically Android programs. And we've gotten a bunch of these that were labeled malicious from our providers, which is kind of interesting. And then lastly, if you, oh, that's off the screen. Let me adjust this. That's weird. Sorry about that. So you can't see it. I'm not sure why it's cut off here. but this is the actual detail page. So if you were to click any of those search results, this is what you'd see. So it shows, which is cut off really everything we know about this piece of malware. So in this case, we have ClamAV, we have PE frame, we have Yara, and we have PE hash. Let me just scroll down. One thing you might notice is this data is very tabular. We did that really just for the sake of exploration, so you can look through the data that you have just extracted out of the malware and view it in a tabular form. We also expose raw JSON for all the data, so you can see it in its original structured form. This allows you to write application. If you wanted to write an application on top of this, you can call these API calls and get the actual raw data that backs it. You can also focus in on, if you just cared about the ClamAV data for a specific file, you can make API calls and just get that specific JSON data. Any questions about this web interface or about what we showed you so far? The question is, can we use our own tools such as PE dump? As of right now, if the tool can be written as a script that runs on Unix, so a Python script or a Bash script or really any script that can process malware, you can use it over this system.
You guys mentioned you extracted 500 headers and you said you're in the process of proving them. Features, what things are you guys using to improve the features?
So we're trying to determine what the highest entropic features, info gain, standard machine learning techniques.
Oh yeah, you go for it. Yeah. Thanks.
When you run over those 20 million files in 5 hours, what exactly are you doing with each file? Just like strings or something more complex?
So the question is, what are we doing for the 5-hour marker over the 20 million files? We're currently doing things that are significantly more complex than strings. We're extracting all of the feature elements that we have for that particular one. At that time, I think we had about 400 feature elements that we were extracting from the individual headers. We were extracting individual elements from the the resources, so we're doing actual resource extraction internally inside of the PE file itself, and we were collecting those and reinserting them back into the system. We've got one more back there. We're about to do a wrap-up as well, so this will be the last question before we complete the
Just to follow on his question, your static and your resource extraction, how long does that take for a single app? Versus like you throw it in your Hadoop cluster and you're like, oh, 5 hours. But if it's one app outside of the cluster, how long does it take? Minutes, seconds, hours?
So that will definitely depend on the size of the file itself and a bunch of other things. But on the whole, it's on the order of only, I think we can do it in under a second.
Under a second. Okay,
yeah,
cool.
The majority of it can be done in under a second. Okay, so I'm going to wrap this up real fast. Then we're going to have a little bit more time for questions, and I'm sure everyone's eager to get out because it's been a long day so far. So the big kicker here, as everything goes for BinaryPig, is that it's a framework. And even though the individual elements that we have when we're releasing the tool, Yara, PE hash, PE frame, and ClamAV, are certainly not the height of all that can be done for static analysis, we're releasing them in this format to give examples of what you can do, how easy it is to add new elements, how easy it is to add new things. And that's really what this is for, the ability to quickly add new scripts and new analytics and apply them across a historical data set with very little time necessary to concern yourself with, well, will this scale in this way? Will we run into any kind of contentions for processing this over network? All of that has to be abstracted away so that analysts, researchers can very easily develop new scripts without having to be concerned with those elements. The feature extraction itself is something that we weren't able to do before internally this quickly or this extensively, and it's certainly something that's available now. We hope that it's going to be something that people use to develop new ways of doing large-scale triage. Internally, we've been using it for weekly AV scans as we grab new signatures for various other antiviruses other than just Clam. We're constantly looking at the deltas, evolving what we understand. It's essentially building a historical VirusTotal-like application internally. And then in addition to what we've got here, hopefully we'll be able to open source it or present it as we develop the validation and tightened down everything that we're working on. We've developed a binary classifier that improves our sample collection. That way we're able to very quickly determine whether or not this is something such as adware, true malware, various other things like droppers, and then triage them as necessary before inclusion into our dynamic system. We've got a little future work left to do. Right now we have compatibility with PIG 10 and PIG 11. PIG 12, I'm sorry, let me back up. We have compatibility with PIG 8 and PIG 9. We need to develop compatibility for PIG 10 and PIG 11. We'd like to release an EC2 tutorial very quickly. We've done some of this work over EC2 to store, run historical data sets. To run our entire historical set cost us about $150 for a single query over EC2, and then to run every single day individually cost us like $12. So it's very cheap. If you don't have a Hadoop cluster currently, you're totally able to take BinaryPig and test it out on something that's relatively inexpensive. We need to develop some better error logging and handling. Right now we believe that a lot of our error messages should be stored in separate databases for more robust storage and analysis. Right now we're piggybacking off of Hadoop's own error logging mechanisms. This works, but we think we can do somewhat better. We need to automate some of our deployments. The analytic daemons right now are not automated for deployment, and we need to develop a way for doing that. And we definitely need to develop some ways of pushing out some of the dependency libraries a little easier. The entire framework, as we've shown it today and as we've described it, is open source. The web front end, the analytics, some of the analytics scripts themselves, and the BinaryPig modifications, the Apache Pig system, are all sitting up on GitHub right now. Please do a pull request if you have anything you'd like to change. We certainly are definitely into feedback. So this is pretty much the end of the presentation. I'd love to know if anyone has any further questions. If there's anything that anyone's interested in talking about, we're going to be here. If these are things that you're interested in, we'd definitely like for you to come and chat with us. Anything else? Thank you. And are there any other questions before everyone leaves? Yes.
On your, so you mentioned a malware cluster, 300,000 samples or so.
Yes.
What was sort of the feature set you used to determine what the clusters would be?
So the feature set itself is fairly large, and we definitely need to prune it down. A handful of the features that were included were individual complexities of various sections. We also had features regarding the memory allocations that were outlined in a PE file for various elements of the PE file itself. The number of features for the resources and resource usage inside and size and individual hashes of those files as well. We're hoping to do further validation on the results and release the entire feature set shortly.
That's it.
Hey, there's one over there.
Any other questions? Hey,
Still on the mic. Thanks. I was wondering, so with your clustering algorithm, can you talk a little bit more about, so do you have a distance function and then you have some clustering? Can you talk a bit more about the math or how that works?
We'll take that offline. That would probably be better.
Okay.
That's all right.
Thanks. And I had the same question about your binary classifier, but maybe we'll take that offline too.
Same thing. Yes.
Okay.
I think that's it.
all right, thanks.